This video discusses the use of the root locus design method for designing a lead compensator that will assist in improving the transient performance specifications of a second order system. And what we'll do in this video is try to motivate the need for a lead compensator, and then go through actually solving a problem using at least one method to determine the location of the pole and zero of the lead compensator so as to achieve the desired transient performance or time domain performance. So we have a plant here. On the left here, it's 10 over s times s plus 1. So it has second order, it has a pole at the origin and a pole at -1. And you see the block diagram here where I have allocated space for the compensator. I'm calling it GC of S, but initially we'll just assume it is equal to 1, and when we do that we can compute the closed loop transfer function, which is 10 over s squared plus s plus 10, and from this we can determine that alpha is 1/2 and omega n is the root of 10. This tells us that the poles are complex conjugate poles. They have a damping ratio of 0.16 and a dampened frequency of 3.12 radians per second, and a real part alpha of 1/2 or -1/2 actually. So from this we can determine several transient transient performances. One is the settling time, and if we look at the 2% settling time, that's approximated as 4 time constants, which is 4 over the real part of the closed loop complex conjugate closed loop poles, so 4 over alpha. So that's an 8-second settling time. And then we're also interested in the overshoot, which in this case evaluates to 60%, so a pretty significant overshoot, and we calculate that using zeta, the damping ratio. Now for this, for our eventual system, we have the requirement that that we have a steady state position error. So this is like static. This is error to a step, which means that eventually we want this to settle out and have 0 error, no difference between the reference and the eventual output. Secondly, we'd like a settling time of 2 seconds, so 4 times faster than the system is originally, and we want an overshoot to be limited to 5%, so that must be reduced down from 60%. From these performance requirements, we can start thinking about where we would like the closed loop poles. Now before doing so, let's just recall that for addressing the steady state error requirement of 0 steady state position error, this has to do with the type of the system. The type of the system is the number of pure integrators there are in the open loop transfer function. In this case, our plant times our compensator, which right now our compensator is 1, has a pole already at 0 and a pole at -1. So this system, as it comes to us, the plant has a pure integrator, and so it is a type 1 system to begin with. Type 1, which means that this has a 0 steady state position error. In other words, 0 steady state error with respect to a unit step. It will have a constant steady state error due to a ramp, but our specification doesn't say anything about steady state velocity error requirements. So our system does meet the steady state position error. That's good. We don't have to make any adjustments or add any compensation to achieve that. Even our uncompensated system would achieve a 0 steady state error. The second one, our settling time, puts a constraint on the real part of our closed loop poles. So the real part of our closed loop pole is going to have to be at -2, and currently, as the system comes to us, it is at -1/2, so we have to move that to the left by a factor of 4. Then we can use the overshoot and we can solve for zeta as a function of overshoot. This formula here is worth probably memorizing. The magnitude of the log of the overshoot over the square root of pi squared plus the magnitude of the log of the overshoot squared. And in this case, we need a damping ratio of 0.69, so we have to increase our damping ratio from 0.16 to 0.69. From zeta and from the real part of our closed loop pole, desired closed loop pole, we can find the natural frequency, omega n, to be 2.9 radians per second, and the dampened frequency, which is 2.1 radians per second. So now we have determined where we would like our closed loop poles to be located, and we have to now add a compensator that will move the closed loop poles from their initial position of -1/2 plus or minus j 3.1 to -2. Sorry, let me scroll down so you can see it. From -1/2 plus or minus j 3.2 to -2 plus or minus j 2.1. I have located on this S plane on the right the location of our desired closed loop poles, and notice I drew them a little bit differently than I would normally draw poles as X's on the S plane, because in this case these are not the location of open loop poles. This will definitely confuse some of you. It actually has confused me a couple times. I have to think about what I'm actually looking at. So later when we are looking at like satisfying the angle condition for G of S, in order to locate the root locus at a certain point on the S-plane, remember we look at the angle contribution from all the poles and zeros, right? Adding the zero angle contributions and subtracting the pole angle contributions. Well, you don't need to add or subtract an angle contribution from this desired closed loop pole, because this is not an open loop pole. This is the closed loop pole. This is a point on the root locus. And so I draw it differently, more as a solid dot and then a kind of an X through that. So hopefully that will be helpful to you, as it has been helpful to me. Okay, so what we see here, looking at the left side, is the original root locus plot of the uncompensated system. With the pole at 0 and a pole at -1, and no finite zeros, we have two root locus branches to infinity. Number of poles minus number of finite poles minus number of finite zeros, and that's equal to 2. So we have two root locus paths going to infinity. They have to go at plus and minus 90 degrees because the angle of separation between them is always 360 degrees divided by the number of branches. So in this case it's 360 divided by two branches, so the angle of separation is 180 degrees. Furthermore, the root locus is always symmetric about the real axis, so I have to have the two branches going at plus 90 degrees and minus 90 degrees, any other angle, and they would not be symmetric about the x-axis unless they were lying on the real axis, but then they would violate our rule regarding where the root locus lies on the real axis, and that is always to the left of an odd number of poles and zeros. So here we see that the root locus lies on the real axis only between the open loop pole at 0 and the open loop pole at -1. So this is our uncompensated root locus, and what we need to do is we need to move our the root locus of our compensated system in such a way that it will move to the left and cross through the desired closed loop points of -2 plus or minus j 2.1. And notice that in doing so, the trajectory, or the asymptotes that I want, are still going to be at plus and minus 90 degrees. So I don't fundamentally want to change the number of poles minus the number of zeros. I want to maintain that as 2. All right? So for instance, if I were simply to add a pole, now my system would no longer be My system would no longer have just 2 branches going to infinity at plus and minus 90 degrees. I would have 3 branches, and one would be going, let's see, in this case, one would be going off to the left on the real axis, and then 2 would be ultimately veering off at plus and minus 60 degrees, as it turns out. So I don't want to do that. And if I added just a 0, which is actually what I need to do to bring this root locus toward the left, if I added just a 0, then now I would only have one path, one root locus path to infinity. Let me show you that, because some of you may be wondering, why wouldn't we just do that? It seems like a more simple system. So let's say we have a pole. We have our pole at 0 and our pole at -1. Now if I add a compensator, then, and the compensator is simply a 0. Okay, so let me add a 0. Here's a 0. So, oh, actually, let me add the 0 in a different location. Let me add the 0 right here first. Okay, so now my root locus is going to lie to the left of the pole at 0. It will not lie to the left of this 0 that I've placed, because there's an even number of poles and zeros to its right, but there will be a root locus to the left of -1, because to the right now are an odd number of poles and zeros. So this is what the root locus would appear as. And we might say, well, hey, we can do this. We can position a closed loop pole right here at -2, right? That's good. However, our second closed loop pole is going to sit somewhere between 0 and, let's say this is -1. All right, and I have a closed loop pole that's now going to sit somewhere between these two. Right? Say I'll put it right here. Right? Well, now, what pole is the dominant pole in my system? The dominant pole in your system is always the one, or the ones if it's complex conjugate, that are closest to the j omega axis. So actually this system is going to have a dominant pole that is close. That's actually worse than our system originally, right? Our original system had a real part of -1/2. Now this dominant pole is to the right of 1/2. So that's clearly not helpful. Now, to be fair, we don't have to place the pole there. We could place the pole in, we don't have to place the 0 in between the two poles. We could place our compensating 0 to the left of -1. So let's take a look at that briefly. Okay, and so I have a, let's see here. Okay, so let's put the pole, or the 0, to the left here. Now I'm going to have a root locus between 0 and -1. Oops. 0 and -1. And I'm going to have a root locus to the left of the 0. Oops. Okay. Now it departs from the open loop poles and it ends on the open loop 0. So what's happening here? It means I must have a breakaway, okay, and I must have a break-in somewhere to the left. And what will happen is I'll have some kind of an arc here. Okay. And this obviously looks like a little more complicated of a root locus. But notice that what we can achieve here, we can achieve closed loop poles if we wanted to, somewhere out here, right? So in theory, it would appear that we could move the closed loop poles to the left of -1. We could get them to be at -2. Maybe actually I should show that here. Like this looks more like -2 here. Right. And perhaps I'd have to move it up a little higher if I wanted it to be at the desired plus and minus 2.1 J. But I should in principle be able to do that. Now we're not going to design this compensator, but I'll just point out what is this type of compensator. This type of compensator is let's see, it's going to be a GC that adds purely a 0. Okay, now what is this? Maybe more generally, let me write it like this. If you have done anything with controllers before, you would have heard about, probably about PID controllers, right? Proportional, integral, and derivative control. And this compensator here has a derivative element and it has a proportional element. So this is a PD controller right here. Proportional derivative, no integral, but proportional derivative controller. And it's possible to design a proportional derivative controller that would move your closed loop poles to the left of -1, and perhaps even to even to meet the zeta requirement of 0.69, so that we can limit our overshoot to 5%. We could do that. Now I'm not going to dig into that at this point, so I just wanted to mention this so that you realize that there are definitely more than one way, one approach to design a compensator that meets the requirements. But I'm going to argue that in this case, designing a lead compensator is going to be the easiest method, the most straightforward method. So let's get into designing the lead compensator. Okay, we now want to get into designing the lead compensator for our system. That involves this plant having a pole at the origin and a pole at -1, and I've located them here on the S-plane right here. And I've also located the location of our two desired closed loop poles, which will meet the transient specifications that we have started out with. So what we're going to do is we want to consider the angle condition of our system, our open loop system, at that desired closed loop pole location, and determine what kind of angle deficit do we have, which we will have to accommodate using our lead compensator. So we have GP is equal to 10 over S times S plus 1. We have the overall forward gain, G, is the product of GP and the compensator GC. And the angle of G evaluated at the desired closed loop pole location right here is equal to the angle contribution from GP, our plant, plus the angle contribution due to our compensator. We haven't designed our compensator yet, so what we're going to do is we're going to put a placeholder here. We'll call it phi of C, the angle that will be added or contributed, the leading angle that will be contributed by the compensator at, specifically at this desired closed loop pole location of -2 plus 2.1J. And for the angle of GP, we've seen before that we add up the angle contributions from each pole and each zero. Now in this case we have no finite zeros, so we have a pole at the origin, we'll call that theta 1, and we have a pole at -1, we'll call that theta 2. So we have minus theta 1 minus theta 2 plus phi, and this must all equal some odd number or odd multiple of plus or minus 180. So I'll just write it as plus or minus 180. We then are going to solve for the angle deficit, the amount of lead angle that the compensator will need to provide at this desired closed loop pole location. So it'll be equal to plus or minus 180 degrees plus theta 1 plus theta 2. So now we need to go to work at figuring out what theta 1 and theta 2 are. Turns out that theta 1 is is related to another interesting or of interest angle, and that is beta. We've encountered that before, so let me draw that out here. Here's our closed loop pole position, and this angle here we've called before beta. It is related, beta is equal to the arctan of omega d closed loop divided by alpha closed loop, because after all the horizontal is alpha closed loop and the vertical is magnitude omega d closed loop. But beta is also equal to, or can be shown to be equal to, the arc cosine of zeta, which in our case for zeta equal to 0.69, beta equals, let me check here, 46.4 degrees. Okay, now this angle theta 1 here is just equal to pi minus beta in this case, and the angle theta 2 is related to the inside angle here. I'll call theta 2 prime. So let's go ahead and write this. Theta 2, we can write theta 2 is equal to 180 minus theta 2 prime. 180 minus theta 2 prime. And yes, and then we have for theta 1 we have pi, or 180 degrees, minus beta. Okay, and now for theta 2 prime, let me write that over here. Theta 2 prime is equal to the arctan of omega d closed loop divided by this distance right here, which is going to be alpha closed loop minus 1. Okay, and let's see, that evaluates to let's see, we have 2.1 for omega d, and we have 2 minus 1. Take the arctan, 64.5. 64.5 degrees. So now we can write that we need plus or minus 180 plus, really we have 360 here, minus, we said beta was 46.4 degrees, and then we subtract 64.5 degrees. So let's do 180 minus 46.4 minus 64.5. So 180 minus 46.4 minus 64.5. Is that right? 69.1. That doesn't look right. So we've determined that the amount of phase that needs to be contributed by the compensator at the desired closed loop pole locations of minus 2 plus and minus j 2.1 is 69.1 degrees. And I've called this phi of C, C for compensator. But now I regret having done that. I want to rename this to phi lead. I'm going to call this phi lead. So we need 69 degrees of lead angle in order to move the root locus to the point, or to pass through a point at -2 plus j 2.1. Okay. Now, the next thing we have to do now is to determine where to place the pole and zero. So I've placed just arbitrarily a pole and zero in red and blue here. Now, for it to be a lead compensator, the zero has to be to the right of the pole. This is obvious just geometrically here. We see that we have an angle phi c. Okay, so this is not what I'd called phi c earlier. That's why I wanted to rename this to phi lead. Phi c is the angle contribution from the zero of our compensator, and theta c is the angle that we lose due to the compensator pole that we place. And we can see graphically here that the angle of phi c is greater than theta c, and this leads to it being a lead compensator, which is what we need. So if we needed a lag compensator, we'd switch those two. Now, it turns out that if you do the geometry here, that this angle in green is actually equal to the lead angle. Okay, so we could stretch, let's see, we could stretch our zero out. We could make our zero, say, go to here, and we could move our pole, stretch it out to here. Okay, so as long as, I don't know that I drew that well, but as long as this angle here is still phi lead, and these are equal to each other, we can position the pole and zero really at any location. And there is a limit. Now, there is a limit to how far left you can place the compensating zero, because at some point the angle that is added by phi c is going to become smaller than the lead angle that we actually need to provide. So we can only go so far left, and I'll let you derive that, but anyway, we're not going to try to push it out to the left. There's two approaches that are described in the book. The second method is one that actually I'm going to show you first, because I think it's more, it's easier to carry out. And for this, let's go back to the plant, or actually the forward gain of G equal to GP, which is 10 over S times S plus 1 times our compensator. Our compensator now is going to have some kind of a gain times S plus a compensator 0 over S plus a compensator pole. And maybe I'll put, yeah. So what we notice is that I could conveniently place this 0 here. I could move it, I've shown it, I could move it to the right of where I've shown it, and I can move it to the left. If I move it to the right, then the angle that it's contributing keeps growing. It'll actually grow past 90 degrees, become larger than 90 degrees. But that's okay, because I can move the pole out to the left, or move the pole in, I should say, close to it, and we can still get a difference of between the two angles that's equal to the phase lead that we're trying to achieve. So the second approach that the textbook shows is to place the compensating 0 right on top of the open loop pole at -1. Okay, let me show you that. We'll redraw this. So we have a pole at 0, a pole at -1, and we're going to put the compensating 0 at -1, and then we will put let me see, move this in a little bit. And then we'll put the pole out further, somewhere out here. Okay, so let's draw our desired closed loop pole locations right here. And what we get is the actual pole and the 0 cancel each other. Well, how does that work? Well, if we let the 0 here equal -1, then I get let it equal +1 here, s plus 1, so the pole is at -1. Then I get the s plus 1 in the numerator to cancel with the s plus 1 pole in the denominator. And this results in a transfer function that is now just 10 over s times s plus p c, the compensator pole location. So that simplifies things, because now I really only have two angles to account for. So I have the angle here, which I'll call theta c, and then I have the angle from the pole at the origin, which we've described before is theta 1. So our angle condition now becomes angle of g of s, this is at the closed loop pole location, is going to be equal to minus theta c minus theta 1 is equal to plus or minus 180 degrees. So minus theta, or I should say plus theta c, is going to be equal to plus or minus 180 degrees, or minus plus 180 degrees, minus theta 1. Theta 1, we had found earlier, was, well, theta 1 is pi minus beta. So theta c is equal to plus or minus 180 minus pi minus beta, which beta is 46.4 degrees. So we end up getting a theta c that's equal to 46.4 degrees. Now we could have seen this anyway because it's a isosceles triangle, right? So we can just graphically see that this pole location here is going to have to be at -4, so that we have an equal distance here to, as we do here. Right. So we can therefore say that our compensator, G compensator, is equal to some constant times a 0 at -1 and a pole at -4. We need to now find not G of C, we now need to find K, the constant out in front. So to do this, we have to satisfy the angle condition. The angle of G of S is going to be S equal to the closed loop pole location. Needs to be equal to 1. Well, that's equal to K. And then we have, well, remember we have the simplified transfer function right here because of the pole 0 cancellation. So we have K times 10 over the magnitude of -2 plus J 2.1 times the magnitude of -2 plus J 2.1 plus our pole location of 4. Therefore, K is going to be equal to magnitude, let's just work this out, the magnitude of first term here is 2.9, and then our second term is going to be, what is it, 2 squared, which is 4, plus 2.1 squared. Take the square root is also 2.9. I should have seen that because these are equal, or isosceles, equal sides. So we end up getting 2.9 squared over 10, which equals 0.841. Okay, and now we can say our compensator is equal to 0.841 times s plus 1 over s plus 4. And that is our lead compensator. Now we need to go check whether or not our system really does behave as desired. So I have a MATLAB script here, and I will, let's take this one out for now. Okay, so I have the original system, which is 10 over s times the quantity s plus 1, and the sys0 is just the closed loop system involving no compensator, just the plant. I should have called GP there. The system 1 is where I've added in the lead compensator here. You see 0.841 times s plus 1 over s plus 4, and I use the feedback function here to build a closed loop or closed loop transfer function using the forward gain and then the feedback gain, which is 1. It's unity gain feedback. I have a second system here also that I might as well, no, we'll leave it out. We'll maybe talk about afterwards. Let's go ahead and run this and see what we get. So here's the response, and the uncompensated system is this blue. We see that it has an overshoot of 1.6, which we had actually predicted. Where did we predict? Yeah, 60% overshoot right here, 1.6. We're expecting a settling time of 8 seconds. So we can right-click characteristics. We can do peak response and settling time. And we see for the original system, the settling time is 7.3 seconds. Okay, which is very close. I'm not sure if they use so the 4 time constants is an approximation, so that's why there's some discrepancy here, and I'm not sure. I think they're using the 2% criteria here for the in MATLAB, but we're on the same order of magnitude here, right? The settling time for our second system, our compensated system, is 2.047, which is what we wanted. We wanted a 2-second settling time, and we also, furthermore, wanted to have an overshoot of 5%, settling time of 2 seconds, overshoot of 5%, and we see the overshoot here is 5%. So our design has been successful at improving the transient response, the settling time, and the overshoot. So that's how you design a lead compensator. And the main rule, again, to recap, that was used in ultimately positioning the pole location, the pole 0 location of the compensator, was to position the 0 of the compensator to be on or to the left of the leftmost open loop pole. So let's look at another case here real quickly just to reiterate this. If we had a system that had a pole at -2 and say a pole at minus 0.5. Okay, then when we added in our compensator, actually let's just keep it at 0 here. Okay, so the system hasn't changed in its nature. But what we'd do is we would put our closed loop, or our compensating 0, on top of our leftmost open loop pole, and then we would choose our closed loop, or compensating pole, to be whatever position to the left that was necessary to meet the angle requirements. Now we could have moved this slightly to the left, and we could solve that as well. And let's see if we did something like that. Let me go ahead and put this back here. We have minus 1, so that's the system we're working with, and we want our closed loop pole to be at minus 2 and 2.1, about right here. And let's say we put our pole, our 0, just to the left of this. Let's say we placed it at, well, let's say we placed it right here at minus 2. Okay, so we contribute an angle phi of c equal to 90 degrees. We still have our angles of theta 1 and theta 2. Right, and now we're going to place a pole out here that will contribute a theta c. So we have that theta c is going to have to equal plus or minus 180 degrees, and then we will subtract phi of c and we'll add theta 1 and theta 2. Let me pause the video and plug in the numbers here. I got to get theta 1 and theta 2 again, then I'll restart. Okay, actually I messed up here. Took the long way to try to find the angle theta c, the angle contributed by our compensating pole. Actually, we know that the lead angle that we need is 69.1 degrees. That remains the same, but that comes about from taking the difference between the angle contributed by the 0, which we know in this case is going to be 90 degrees, minus the angle contributed by the pole, which is what we're solving for. So that gives us an angle contributed by the pole of 20.9 degrees, or it'll be minus 20.9 degrees. We then recognize this triangle here, and we can solve for this pole location by doing the tangent of this angle is equal to the height, omega d closed loop, divided by the horizontal run, which is the pole location PC minus 2. And solve for PC, and we find that PC is equal to 7.5. So therefore, we have a compensator that is equal to K times S plus 2 over S plus 7.5. And we need to find K again. K is now going to be equal to, remember the magnitude condition, it will be S times S plus 1 all over 10 times S plus 7.5 over S plus 2, all of this evaluated at S equal to minus 2 plus J 2.1. So this is magnitude of all of this. So I'll pause the video and calculate this. Okay, I've calculated K, and we need a gain of 1.895. So our compensator becomes 1.895 times S plus 2 over S plus 7.5. And let's check with MATLAB to see what our performance is. So I've put a second system in here 1.895 times s plus 2 over s plus 7.5, and we'll plot that along with the previous systems that we've already looked at. So here you go. If we turn on the settling time, we see that the settling time for our new system, which is the lighter color yellow, is around 1.95. So that's good. What about our peak response? Well, that's not as good. Our peak response previously was a 5% overshoot, and now our peak response has a 17.4% overshoot. And that's disappointing and puzzling because we designed our compensator based on a transient requirement of 5%, locating, based on that, relating those to the requirements of our closed loop pole location, mainly the damping ratio, zeta closed loop, and the real portion of our closed loop pole location. And so it would seem that we should have an overshoot of 5%, but we don't. And let me try to give a little insight on this. It's a little bit of unfortunate news. It means that there's some trial and error needed here. You could develop more analytical tools and procedures to compensate for this, but at some point you decide just to iterate. So let's consider our first system here. That was designed based on placing the zero. We have zero pole cancellation. Remember, we canceled the pole of the open loop system with our zero. So when we write out our forward path gain G of S, the S plus 1 and S plus 1 cancel, and we end up with the G of S that is pretty simple. And the closed loop transfer function is of this form here. So it's 8.41 over a second order term. Notice no finite zeros. No finite zeros. For our second system, though, we have a different situation. So this is the case where we did have the overshoot was 5%. 5% overshoot as required. In our second case, we have a G of S that is 1.895 S plus 2 over S plus 7.5 times 10 over S times S plus 1, and we get no cancellation. So we end up with 18.95 times S plus 2 over S times S plus 1 times S plus 7.5. Now notice in general, if G of S is equal to some numerator polynomial over a denominator polynomial, then the closed loop transfer function is forward gain G of S over the loop gain 1 plus G of S. But that can be rewritten as the numerator N over D, all divided by 1 plus the numerator over D, and then we multiply everything through by D, so we end up with D plus N in the denominator. And this is an important observation, mainly that the open loop zeros are or become the closed loop zeros. In other words, they don't change. Okay, so what we're seeing in this first case, where we canceled our 0 of our compensator, the s plus 1, canceled with the s plus 1 in our plant. Our open loop gain right here had no zeros, no finite zeros. And so the closed loop transfer function here also had no finite zeros. And you might say, well, what does that have to do with overshoot? Well, if you recall, when we derived the transient characteristics for second order response, we used a transfer function of the form like omega n squared over s squared plus 2, what was it? Well, we might have done alpha plus omega n squared, right? Notice no zeros. This led to zeta, and it led to, I should say, the overshoot, the rise time, etc. Right? And that was predicated on there not being any finite zeros in our closed loop system. And that's exactly what we have for this first case, where we canceled the 0. Our 0 in the compensator was canceled by a pole in our plant. But in the second case, notice that our transfer function here does have a finite 0. So what will happen is that in this case, in the second case, g of s is going to be equal to some constant times s plus 2 over now whatever our denominator is. So we've added a 0 in the numerator. And what does that mean in the time domain? If you think of g of s as equal to s plus 2 times some constant over a second order term here, second order term, then this piece here is going to have the nice overshoot of 5% as desired. When you multiply by s plus 2, what's going on in the time domain is a derivative with respect to t and then a constant term. Right? So we're taking this right here and we're going to take the derivative of it and we're going to multiply it by 2, and then we're going to put them back together again. And now we end up with something that actually has an overshoot that's higher, greater than 5%. Okay, so things aren't quite as clean when we have finite zeros in our closed loop transfer function or in our open loop transfer function. And what you end up having to do is you have to design for the overshoot to be smaller than you would desire or need in order to try to actually achieve the overshoot that you're really looking for.